Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Listeners have asked us to provide pointers to some of the resources we talk about on the show. We now have links to books and articles referenced in recent podcasts that are available on our website. We also offer full transcripts. Go to jimruttshow.com. That's jimruttshow.com. As regular listeners know, I'm pretty obsessed with the Fermi-paradox and often ask our guests their views on it. Well, today we're lucky enough to have as our guest Stephen Webb, author of If the Universe is Teeming with Aliens, Where is Everybody? 75 Solutions to the Fermi-paradox and the Problem of Extraterrestrial Life. I actually read an earlier version with 50 solutions, I don't know, back in the double aughts sometime, and that actually is what triggered my obsession. You know, typical nerdy 14-year-old, I assumed there had to be at least 10,000 civilizations out there in the galaxy. But reading that book, I became much more skeptical and much more of an agnostic on the thing. And when people give me their answers on one side or the other, I have this long list of refutations in any direction you'd like, right? But anyway, he has updated the book with 75 solutions. I think he dropped a few, it looked like, and added some new ones. So we're going to talk about that today. Welcome, Steve.
Jim, it's a pleasure to be with you, and thank you for inviting me.
I've been really looking forward to this because, seriously, this is one of my true obsessions. I believe that the answer to the Fermi paradox is the second biggest question in science, of course. That begs, what the hell is the first?
Indeed. What's the first?
In Ruttian doctrine, it is why something and not nothing. In other words, why does the universe exist?
At all? Yeah, that's a good one. I think it's a question that physicists will eventually make some progress on, and I'm getting old, and before I shuffle off this mortal coil, I'd like to see an answer to that. I'd really like to see an answer to this question about the role that biology plays in the universe. I think that you're saying it's the second most important question. For me, I think we might get more progress on that first before we get progress on the second, and I'll explain why later.
Yeah, I believe you're likely correct. Before we jump into it, I wanted to mention that Stephen's got a PhD in physics from University of Manchester, and at least in his old age, has been a writer of pop science books. He has 11 books out. A new one coming out in October that looks quite interesting. So, to start out, what is it that we mean when we say the Fermi paradox?
Okay, so it dates back to the summer of 1950, where Enrico Fermi, who was one of my favorite physicists, he's a hero to lots of physicists because this guy could do anything. He was a great theorist. He was a great experimental physicist. He had this fantastic ability to make estimates of quantities in his head. Just ballpark figures, we would call them. Even if you don't seem to have enough information, he'd be able to get a rough idea of the order of magnitude of a solution to a question. Anyway, Fermi, one day at Los Alamos, one summer's day, was discussing UFOs. I believe there were a lot of them at the time in America in the early 50s. And out of the blue, at lunchtime, while they were discussing this question, he just asked, where is everybody? And because it was Fermi, the guys he was having lunch with realized it was actually quite a profound question. And the reason it's puzzling is because it puts two things into tension. So on the one hand, we have the fact that the universe is big. There are lots of places for life, presumably, to get going. And we can even estimate how many civilizations might be out there. The usual way of doing that now goes by the name of the Drake equation. It's not really an equation. It's, as some people say, it's a way of organizing our ignorance about these questions. But essentially, you make estimates of various quantities and you multiply them all together and you get an estimate for n, which is the number of communicating civilizations. Now, that's the sort of thing that Fermi was brilliant at doing in his head. So he'll have come up with an estimate for n, the number of civilizations out there. And the Drake equation, just for your listeners who might not have heard about it, it's a number of terms. It's the rate of star formation.
We're going to get back to all those things here in a minute. But first, let's take a little sidebar in your mention about UFOs. I think this is something we both agree on, is that for the purposes of this analysis, we're going to discount to zero the claims of recent alien visitations, such as UFOs, the claim that some of our politicians are shape-shifting lizards, despite the fact some of them act like it. Obviously, their probabilities aren't actually zero, but they're probably pretty close. And in any case, there's no solid evidence one way or the other and kind of doesn't belong at this point within a scientific discussion. In fact, frankly, I believe a lot of it belongs in the domain of abnormal psychology. One of my favorite scientific quote-unquote statistics was John Mack, who was a researcher at Harvard, did a big survey of Americans, and 2% of Americans claim they personally have been abducted by aliens.
That is probably the most commonly accepted resolution of the paradox, I guess, that they're out there buzzing around and interfering with our everyday lives. Science isn't a democratic process, though.
Yeah, so today we're going to ignore that, and we're going to assume that is mob hysteria, abnormal psychology. Might not be, but that's what we're going to assume for today. So one of the things that has kept me obsessed with the Fermi-paradox is how many different scientific disciplines you have to know at least something about to think somewhat clearly about the question. I took some notes as I was reading, and here's a list of scientific disciplines that were in passing at least mentioned, and there's probably more that I missed. Astronomy, astrophysics, cosmology, physics, chemistry, geology, planetary science, biology, biochemistry, genetics, evolutionary biology, astrobiology, and then even in the social sciences and humanities, a fair bit of need to understand economics, psychology, sociology, philosophy, history, and linguistics. It's amazing.
It is, and I think that's, for me, one of the most fascinating aspects of this question. The other aspect of it is that everyone can contribute. So there are Nobel Prize winning physicists who write papers about this stuff. But I had an email from a trainee plumber this week who was thinking about these things, and he said, "This is my solution." And from that entire spectrum, you can think about this problem and you can make a contribution, which I find amazing. It's one of the few scientific questions where that's still possible.
That is interesting. It allows, professional bullshitters like me to speculate.
I think you do yourself down. Our knowledge of this subject is so varied. So going back to that idea of the Drake equation, there are terms on the left-hand side that are pure astronomy and we're getting really good values for. But there are terms at the outer edge where the only response is a shrug and who knows. And I think your insights into those sorts of questions are equally valid compared to the Nobel Prize winning physicist.
It is true. I have actually had discussions with some of the world's leading thinkers in that domain, particularly around origin of life.
Mm-hmm.
One of the people that dragged me into complexity science was a guy named Harold Morowitz, who was he passed away recently, but prior he was one of the top scientists studying the origins of life. And I've had conversations with Stuart Kaufman on the topic, and Eric Smith, another amazing scientist that works in that area. So that is one where I actually know a fair bit, and it's probably one of the most interesting ones, as we'll get to. But anyway, before we get to that one, let's take a moderate-paced walk through the pieces of the Drake equation. If you don't have them at your fingertips, I can read them off for you.
Yes, Drake equation. And this is the sort of thing I think that Fermi would have gone through in his mind. So it's the rate of star formation, how many stars form per year. This is an astronomy question, and in the 75 years or so since Fermi asked that question, where is everybody? This is the sort of research program that astronomy has developed, and we have good numbers for that. You multiply that, the rate of star formation, by...
Oh, by the way, the value is something on the order of 2, 3, 4, something like that, stars per year, which is actually kind of interesting how low that is. But, of course, you multiply it by 10 billion years and you get a lot of stars. And there were more stars made per year in the past.
And next term would be fraction of stars with planets. Now, when I was a student, I had access to textbooks that said that maybe planetary systems are rare. Maybe you get planetary systems when one star makes a close approach to another star and drags material off. And that's how you get planets. If that were the case, that's actually a potential resolution of the paradox, because there wouldn't be many planetary systems. We now know that pretty much planets are a natural concomitant of stars. If you've got a star, pretty much you'll have planetary systems. The next term in the Drake equation, or the classic Drake equation, would be the number of those planets with an environment that's suitable for life. You multiply that by the fraction of planets where life actually gets going. Multiply that by the fraction of planets where intelligence makes an appearance. Multiply that by the fraction of planets where civilization, technological civilization, gets going and wants to communicate. And then you multiply all that by the lifetime of those civilizations. How long are they going to spend in this pursuit of making their presence known to the universe? So lots of terms, you can add more, but essentially you mash all those together, multiply them, and you can get an estimate for how many civilizations are out there.
Let's clarify that it's not actually the number of civilizations out there. It's the number of civilizations that are actively or could be communicating, could receive a message from us or send one. As we'll get to, some of them may have just turned in and be gazing at their belly buttons for eternity. It's certainly possible. And the other thing, of course, because it's a multiplication of cross, if any of them are zero, the answer is zero. If any of them are small, the answer is small. If several of them are small, the answer is one or less. And it is interesting that I asked Perplexity, which is probably the best AI-aided question answering engine out there. In fact, I'm having the CEO of Perplexity on next week. I asked Perplexity, said, based on the Drake equation and current knowledge, what do you think the answer is? And it came out with, and it's called these conservative estimates. I think one of them isn't too conservative. It said 2 stars a year, which is about right. Half the planets have stars. That is probably conservative. 1 is probably closer to it. Now, this one I think it was actually liberal on, which is 1.5 stars in the habitable zone per star. It may well be less, something on the order of 0.4. The fraction of planets that actually developed life at some point, it gave 0.1%, which is in the range people talk about, but maybe real high, maybe real low. We don't know. It's not a crazy number. The fraction of planets with life that go on to develop intelligent life, it said half. Seems high to me, but hey. And the fraction of civilizations to develop a technology that releases detectable signals, it said 0.1, whatever. Length of existence in the communication phase, 1,000 years. When I was a kid, I would have said, well, it's got to be at least millions, probably billions. But as I've grown up and seen how stupid our society is, despite our level of knowledge, 1,000 years might actually be not so conservative. You multiply those together, and you say those are not crazy numbers. The number you get is only 7.5. So 7.5 communicating civilizations, so call it 8 in the universe. I then did a little bit of simple math using a disk rather than an actual model of the galaxy. And the mean distance between them, if they were evenly speckled around, would be about 30,000 light years, which is really quite interesting. So a moderately sensible application of the Drake equation doesn't come out with 100,000. Though, of course, you could change those terms. I mean, all of us who've been business dudes and use spreadsheets know there ain't nothing better for lying than a spreadsheet, right? You change a few terms and you get the answer that you want. And I tried a few other ones. I gave some more conservative numbers, and I came up with 0.2. I created some more liberal numbers, particularly lengthening the lifetime to 1 million years, and I got 200. And then the other thing that's worth considering, if you then take even these relatively small numbers and say, all right, our galaxy is more or less like other galaxies, and there's 100 billion galaxies, you end up with huge numbers in the whole universe. And then we'll talk later about whether that really matters.
I think that's a really interesting observation you've made there, Jim. So the paradox potentially goes away just by choosing those numbers. But equally, you can make some optimistic, let's call them optimistic scenarios, and come up with really quite big numbers. And that's what Frank Drake did back in the day. It's what Isaac Asimov did. He wrote a book effectively based on this equation. It was called Extra-Terrestrial Civilizations, and he came up with a huge number. And that's why I think Jill Tarter is the person usually you attribute this quote. It's a way of organising our ignorance, this equation, because pretty much, garbage in, garbage out, we don't know the answers or the values of these quantities, particularly at the right-hand side of that equation. You can get small numbers. I would tend, in my analysis, to come up with small numbers. But if you were to say there's lots of civilizations out there, the Drake equation allows you to say that.
And that's when you get the paradox. If there's only 8 and they're 30,000 light years apart, they only last 1,000 years, there's a lot of reasons why we might not be seeing them. But if you run the numbers, I vaguely recall reading the Asimov book, they would come up with 100,000 or something like that.
Yeah, it's something big. Yeah.
Yeah, and then in which case, then you have the paradox. Well, where are they? God damn it. Oh, and speaking of Jill Tarter, she was one of my earliest guests on the Jim Rutt Show, and I barely knew what I was doing. Back in episode 14, we talk about her life and her work and her thinking. I will say she was extremely cautious in any kinds of speculation. So while an interesting conversation, I think this one's going to be more interesting. So before we actually leap into some of the 75, we're not going to have time to do all of them. Let's talk about 4 principles that come across in the book. I'm going to read all 4 of them, and you can, sort of answer them one at a time or all at once, however you want. The first is the weak anthropic principle. The second is that the time to spread a civilization across the galaxy could be pretty fast, on the order of a few million years. The principle of mediocrity, and diversity arguments, particularly when people talk about sociology or economics. I kind of extracted that 4 classes of deep principles that keep turning up again and again. So maybe give the audience a quick definition of what you mean when we talked about the point about, let's start with the weak anthropic principle.
So, well, there are a variety of anthropic principles, and I don't know if you've ever covered these in one of your podcasts, but you could certainly do an entire podcast on anthropic principles. There are a variety of them, but in essence, the point I would try to get across to people is that we are here. We know we are here. And when we observe the universe, it is difficult to make strong conclusions based on the fact that we are here. So let me give you a specific example of what I mean. A lot of people say that life must be very resilient. Life on Earth is incredibly resilient. And they can point to episodes of Snowball Earth. They can point to mass extinctions. They can point to the fact that the sun's luminosity might have changed over time, and so on and so on and so on. Lots of events that could have caused the destruction of life on this planet. And then they deduce from that life is resilient. But we are here, you know? So when we look back, we cannot look back on an event that caused all life to go extinct because we are here. So there's this selection effect, this observer effect, which is not quite the same thing as the weak anthropic principle, but time and again, as I read the literature, I see people making claims about something, and the fact that we are here lends you to at least question their conclusion. Let me give you another example, if I may. There's a claim that life must be trivial to start life on a planet because it happened really, really very quickly here on Earth. As soon as conditions allowed, life began. But if it takes a long time to develop an intelligent species, if it takes a long time, we have to find ourselves on a planet where life started early from the very fact that we are here, because, you know, we're making that observation. So we have to be very careful when there's only a single example of this phenomenon, which is intelligent life, and we're that example. We have to be very careful about claims that we might make.
Yeah, in fact, I must say I've read some weak anthropic principle arguments on the Fermi-paradox question. And generally, they seem to me like philosophers hand-waving and not really solid arguments. These kind of arguments, they sound good, but they don't taste good, right?
The completely ridiculous anthropic principle is...
CRAP, completely ridiculous anthropic principle. Now, and it's the reason why I mentioned just the weak one, because the strong one, I just don't buy at all. I mean, that's not even science. That's theology or something, and we're not going to be talking about that today. So the next one, and this is one that I did not know about until I read your book 20 years ago, which is there's perfectly reasonable arguments that if there were a space-going civilization, even one that's not much more advanced than we are today, it would not take that long for that civilization, with some reasonable caveats, to spread itself across the whole galaxy, like on the order of a few million years.
So there are different approaches to this in the literature. So you will still see in the literature authors who will say that we can explain the Fermi-paradox by saying that there's logarithmic growth, that it takes such an awful long time to get from star to star. There's a counter argument to that, which Armstrong and Anders Sandberg made a few years ago. And they said if you can get to a type 2 Kardashev civilization, perhaps I should briefly explain what a Kardashev civilization is. So a type 1 Kardashev civilization has at its disposal the entire energy output of a planet, essentially. So humanity would be sort of 0.78 on that scale. A type 2 civilization has the entire energy output of a star, its star at its disposal. Typically, the way you imagine that happening is by that civilization creating a Dyson swarm, which is, now this sounds science fiction-y, but nothing I'm going to say is counteracting the laws of physics. So you would dismantle Mercury, say, if we were to do this. Sounds crazy, but it actually wouldn't take that long if you decide you're going to do this. You use the material to create lots and lots of satellites, if you like, orbiting at 1 astronomical unit around the sun, and then effectively you can trap all of the sun's output. And you then have vast amounts of power at your disposal. Now, what Armstrong and Sandberg calculated was that with just 6 hours of all of that power, the 6 hours of energy output from the sun, you could colonize the galaxy but not just the galaxy, quite a distance, actually, into the local universe. And you do this through self-replicating probes. So you don't send something out at random. You send these probes out to nearby stars, and effectively you tell them, rinse and repeat, do the same thing, rinse and repeat. So it's a directed expansion through the universe. Now, I'm not saying this is likely. I'm not saying it is even something we should aspire to doing. But if there's lots of civilizations out there, it just needs one of them to decide this is what we're going to do. And with 6 hours worth of output from a star, you would have enough energy to get through the galaxy and, in fact, do the same thing in neighboring galaxies.
That's pretty amazing. And it wouldn't take long either.
I suppose it depends on how you define long, but certainly on a cosmic scale, it's an eye blink. It's millions of years just to reach other galaxies. So we're not talking in any way, shape or form about superluminal travel. We're obeying at all times the laws of physics. But on a cosmic timescale, you can do this really very quickly. So some authors will argue that, no, this is going to be a long, long stretch, that logarithmic growth explains why they're not here. But someone like Armstrong or Anders Sandberg would say, well, no, if a civilization wanted to do it, they could get out there quickly.
Another principle that is widely used in science, not just in big space science, and that's the principle of mediocrity.
So we have another way of saying this would be the Copernican principle. It's a principle that has served us well as scientists since the times of Copernicus, which is essentially just saying there's nothing special about us. If you want to say that there is something special about us, about Earth, then that's a potential resolution to the fermi-paradox. And there may be something special about us. But in the absence of any other knowledge, you have to say that our solar system is average, our part of the galaxy is average, our galaxy itself is average. Now, of course, we are on the surface of a planet, which is a very, very different place to being out there floating in space. But on the broadest levels, the principle of mediocrity is a way of trying to make sense of what we see when we make observations in the universe, and to try and extract universal principles rather than just say everything is a special case. We have the law of gravity rather than fairies blowing on things to make things drop to the ground. We have universal principles in science.
Though, as we'll find out later, that can be misleading in some of these
cases. It could be misleading, absolutely.
It's not a law, it's sort of a heuristic, essentially, right?
It helps us in science. It may well be wrong, and it may well be, in cosmology, for instance, that it's leading us in the wrong direction. But as a heuristic, it helps us make progress.
All right, let's hop into this, and we'll leave other definitions for as we need them. And then I'm going to skip through the list of 74 plus 1, leave room for the plus 1, and I'm not going to talk about anywhere near all of them. I'm going to talk about a few of them. Let's start with the one we decided we weren't going to talk about. We'll talk about it anyway, because we can also talk about it from a more scientific perspective, and that is that UFOs indeed, or aliens, are here, and they're watching us, or they have visited us and left evidence, but we just haven't found either of those two yet.
So one of the fascinating aspects of working in this field is that the solutions keep on coming. And if there's ever a third edition, there's certainly enough material for 100 solutions. I can't believe anyone would want to sit through them all. So I need a different way of organising this. But one thing that's happening sometimes is that there's a modern spin on an old solution. And I think that's the case with UFOs. I think there's a modern take on that. And they tend not to be called UFOs anymore, but UAPs. And I believe the proper acronym now is Unidentified Anomalous Phenomena. And I think the US defense bodies, that they're actually quite wise in calling this unidentified anomalous phenomena rather than unidentified aerial phenomena, because we don't know where they're taking place, these phenomena. We do know that people, very sober, highly trained people, are seeing things. You've got jet pilots seeing things. But exactly where is that anomalous phenomena happening? I mean, it might be happening behind their eyeballs. It might be happening with some sort of software glitch. It might be happening in all sorts of ways. And I think to call them anomalous phenomena rather than aerial phenomena is actually quite wise of the US defense people. It's also really wise to investigate these things, because if you've got pilots with jets and those jets have got weapons, you don't want them going off firing at something that's not there, for obvious reasons. So I think we do need to get to the bottom of what this UAP phenomenon is. But a all-domain anomaly resolution office was set up a couple of years ago. And just this year, I think it was back in March, they released a comprehensive historical record report. And the director said, there's no evidence that the US government, any US universities, any US review panels has confirmed that any of these sightings represented extraterrestrial technology. Didn't come as a surprise to me, that conclusion. But I think we do need to get to the bottom of just where these phenomena come from. I'm sort of surprised, in fact, that astronomers get asked to investigate this, because their sphere of expertise, if you like, is stuff beyond the atmosphere. They're really good at analysing stuff that's taking place off Earth, maybe less expertise of regarding stuff that's happening in the atmosphere. But there's an example of a solution that's been rebadged, if you like.
Gotcha. And one of the things I just love about this field is new data is always coming in, right? If we really do, let's say we spend $1 billion a year on investigating all these UAPs, we may say there's definitely nothing there, or maybe there is, and then we'd have new data, which is very cool. So let's go on to our next solution. This is a favorite of science fiction, the zoo scenario.
Yeah, so I guess if you've read any science fiction at all, you'll have come across this idea that we are effectively animals in a zoo. That there are aliens out there right now studying us in our natural habitat. There are related hypotheses, such as the interdict hypothesis, which suggests that we are somehow off limits for whatever reason. A problem for me with these hypotheses was actually quite commonly held by some scientists, and it surprises me. I find it very difficult to come up with ideas about how to test this scenario, because whatever we do, if we try and prod a stick through the gap in the railings of our zoo, if you like, and try and get the attention and jab the people who are looking at us, a negative response to this is easily explained away by these people by saying, well, they're so far advanced, they can hide from us. Nothing we can do will bring their presence to light. So I find it quite an unsatisfying hypothesis personally. A related hypothesis which I find equally irritating, but you can imagine certain ways of testing it, is the planetarium or the simulation hypothesis, which is we're just living in someone else's computer simulation. Now, how's that for an example of recency bias?
I think that one we're just going to ignore because, yes, maybe someday we can figure out how to prove or disprove it. But like my friend Anna Solomon's idea is, well, maybe it's high resolution here, but it's like just wireframes in Alpha Centauri. So we send a probe to Alpha Centauri, and then we'll see the wireframes. We'll know it's all fake. But until we have such data, I'm not going to waste my time speculating about it because it's just a rabbit hole. Let's go on to another one. This is the first time I've heard this idea. I don't believe this was in the first book. If it was, I forgot. And that is the light cage limit, which, by the way, I did not find convincing, but nonetheless, it's an interesting idea.
Just the idea that you can't outrun an exponential effectively. So that if the urge to get out into space is driven by increasing population pressure, say, if that pressure increases exponentially, you're not going to outrun it. You cannot get out into space fast enough to outweigh, as it were, all of these people that are coming into being. So that, again, it's an old science fiction idea that if population expansion is unchecked, soon there'll be standing room only on Earth. In practical terms, this doesn't happen. The worries of a few years ago that population pressure would lead to all sorts of disaster seems to be diminishing, and in fact we're seeing population increase leveling off, and in fact, rather than being driven by exponential population increase, some people say that a resolution of the fermi-paradox is that aliens in fact are green. They're very ecologically minded, and if they move out into space, it will be done on a very ecologically green-minded agenda. But the light cage limit says that if you're going to get out there trying to outrun population expansion, there would come a limit when you can't. And it's just to do with the fact that eventually the expansion of population would be moving so fast it would increase at the speed of light, at which point you're done.
Yeah, that's of course it's crazy. As you point out, we're already seeing that even at our level of technology and culture, we're able to bend that curve. I think this also begs a couple other comments, which is, and you do get to this in some of the later pieces, is that the idea of humans migrating to other planets or other stellar systems is quite a stretch, at least unmodified humans. It could be done, but it'd be unbelievably expensive. And for what purpose? We certainly don't know. It's hard to envision any, even with a Kardashev-2 type civilization, where you could push lots of humans across the gap to other stars, enough to make any meaningful demographic difference. You might send a few pioneers, kind of the way the Polynesians did, but the equivalent of mass migration a la Europe coming to the United States in the 19th and early 20th century, that seems a huge stretch, basically.
Yeah, indeed, and we have to acknowledge that certainly with our current level of understanding and our current levels of engineering, getting to the stars is really, really difficult. I mean, I should say before we go on, if I can, I mean, there is another very new example of a solution to the paradox, based on this idea that they are here, or at least have been here quite recently, which is Oumuamua, which was a object that we know came from outside the solar system. So it was picked up about 2017, I think, in telescopes. It zoomed in very, very fast, very quickly into the solar system, and zoomed out. And it seemed to have an anomalous acceleration as it left. And immediately people were thinking, Rendezvous with Rama, the famous Arthur C. Clarke novel. It looked very, very similar to Rama. And one prominent astronomer has said, well, it's an example of a solar sail, in which case we have a techno-signature here, that this was an artificial craft. If it were, well, paradox goes away because we've been visited. I think most astronomers are happy to explain Oumuamua in terms of known properties of known objects. But the really exciting thing is that we're going to see more of these in future when the Vera Rubin telescope comes online. And we might even have flyby missions. I mean, we'll be able to visit rocks that came from outside the solar system. I mean, how cool is that? So that's something to look forward to in the next few years. So it's another example, though, of someone saying that we have been visited, and most of the scientific community saying, probably not.
I hadn't heard about the acceleration as it was leaving the solar system. I followed the stories on the way in, but I kind of didn't follow it on the afterwards. I'm going to have to check in on that and see what people say, because that could be an interesting anomaly.
Again, don't wish to set the agenda for your podcast, but you could have an entire podcast on Oumuamua. It is a very interesting object. It had an undeniably unusual constellation of properties. But I think those properties can be explained in terms of what we know about objects such as comets and ice balls that might be out there.
Yeah, outgassing. I'll look into that. Sounds cool. Now, and these are all in the category of they exist, but we have yet to see or hear from them. One of them is, and this is actually, I think, an interesting big question mark, is what you called solar chauvinists. That we are solar chauvinists, and that we tend to look at sun-like stars and Earth-like planets. But yeah, that's what you need to be at our current level of technology, probably. But tell us why that may be the reason that we're not seeing anything.
So it goes back, perhaps, again to this principle of mediocrity. What we know is that life, as we know it, requires a planetary surface. Now, that's certainly the case for us here on Earth, and it is difficult for us to imagine how it might be not the case in future. I'd encourage readers to look at ideas from science fiction. So, for example, you might want your own personal asteroid, for example. As long as you have an energy source, you have almost unlimited living space there, your own lovely little home. I mentioned before Dyson swarms. It's something slightly different, but you can imagine a Kardashev type 2 civilization having access to all of this energy and doing something that's slightly different in terms of choosing where to live. We are also bound by biology currently, right now. Who's to say where we might be if we survive 10,000 years, 20,000 years, and make that transformation with some other substrate, rather than just the wetware that we are. But if we can somehow combine with for want of a better word, silicon, what possibilities will that open up for where we might choose to live? We might choose to live around black holes. They are incredible sources of energy. You can extract vast amounts of energy from a black hole. So I think another principle, if we go back to ideas of principles, another principle we need to adopt when we think about these things is what I'd call Stapledonian thinking. So Olaf Stapledon was a British philosopher, and he was interested in the long-term future for humanity. What might we be capable of? And Stapledonian thinking requires us to try and imagine what is possible within the constraints of physics. We're not going to talk about something that would fall foul of the laws of physics. So we always stay within the laws of physics. But within that envelope, what might be possible? And if you adopt that idea of Stapledonian thinking, what can you do if you have essentially unlimited amounts of energy? What can you do if the biological constraints that currently are big constraints on us, what can you do if those are relaxed? So it's those sorts of questions, I think, that we need to ask.
Gotcha. And one you mentioned later is we're often constrained by what we think we can do with material things, but if we had very sophisticated nanotechnology, that game changes tremendously.
Absolutely. So that's a classic example. What happens if you can manipulate material at the very, very small scales? Maybe that changes people's motivations, or whatever it is that we would call ourselves if we develop these incredible technologies. Maybe the things we want to do start changing. Maybe we don't want to get out there into space if we can start manipulating matter on a much smaller scale. Maybe, as Richard Feynman said, there's plenty of room at the bottom, and maybe we move inwards rather than outwards.
And that's another solution that you proposed, which is that not only do we turn inward, not necessarily just to nanotech, but maybe we become obsessed with our virtual lives, and that our virtual lives, particularly as our compute capacity and our energy capacity keeps going up, that the virtual world's so much more interesting than the real world.
It's more interesting than the real world right now for me, as I stare out into a pretty awful, wet, drizzly summer evening. Maybe people stay at home and they surf the net.
Yeah, that's certainly a possibility, and that it would be kind of strange and disappointing if that were humanity's terminus point, but not impossible.
I like to think that the spirit of exploration is there in a sufficient number of people that it wouldn't be a solution for us. And I should say all of these sort of sociological type of solutions, they really do strain credulity that every civilization does that. Indeed, every individual does that. One of the things that makes the fermi-paradox perhaps even more paradoxical is if you adopt this Stapledonian approach, you can imagine in tens of thousands of years' time, if we survive and if we have access to all of this energy that potentially we could, it's not just humanity as an individual entity, if you like, that can disturb the universe in a way that other civilizations potentially could detect. But individuals or groups of individuals would have sufficient power to do that. So you're talking not just about sociological solutions that require every civilization to behave in a certain way, but actually every individual in a certain way. And it's difficult because people are different. And who knows what aliens would be like and the motivations that would drive them.
Yeah, particularly if they evolved entirely separately, even trying to envision what their motivations are is very difficult, and to assume that they're all operating under the same essentially coordinated principle, unless there were some already pre-existing galactic government or something, it kind of does seem beyond the credible.
Absolutely, and it's for that reason I'm not a big fan of that sort of approach, but it is an approach that lots of people do publish on.
All right, another one, and this one there's a lot of talk of in the hard-nosed SETI community, is that let's call it the signaling problem. Either we don't know how to listen because we don't understand the encoding, we're looking at the wrong frequencies, etc., or the signal's there, is we haven't been smart enough yet to extract it from the data. So why don't we talk sort of generally about, I think it was 4 or 5 of your solutions, about signal processing and signal capture, and where we may be failing there even if they're out there.
So the discussion we've just had, I think we could say that it's not unreasonable to say that it's too difficult to actually travel. Okay, I've been very optimistic, and I said, I've waved lots of hands and said, got lots of energy, we sent probes out, job done. Maybe it's just really, really difficult to travel. But we know that light can travel over interstellar distances and over intergalactic distances, because that's what astronomy is, right? It's the collection of light that has travelled over those distances, and then we have to, as astronomers, try and process and analyse those signals and figure out what it means. So even if it is too difficult to travel, we should be able to send signals. And the advantage of that is that those signals are travelling at the speed of light. If we're sending electromagnetic signals, by definition, those signals go where you want them to go. You can target them if you're sending electromagnetic signals. And that's the motivation for SETI, right? That you imagine civilizations out there reaching a certain level of sophistication and sending out signals, electromagnetic signals in particular. And there's all sorts of reasons why they might want to do that. They might want to initiate a conversation. They might want to just wave and say, "Hi, we're here." They might want to leave some sort of record of their existence. All sorts of reasons why they might want to do that. So that's the motivation for SETI, which got going incidentally around about 1960 with Frank Drake, looking at 2 stars, Tau Ceti and Epsilon Eridani. And it is like looking for a needle in a haystack, right? So you have to look at the right frequency. Your telescopes have to be pointing in the right place at the right time. There is a vast amount of phase space out there still to explore. Having said that, everything is better in terms of the search since Drake began. I mean, the computing power that you can throw at this problem is just completely off the scale compared to what Drake started with. The telescopes are better. The infrastructure, the general infrastructure, the storage and the networking and the analysis and the rest of it is just completely different world now compared to what Frank Drake started with back in 1960. So a reasonable answer, I think, from the SETI community is that we just have to listen longer. And it might take another few decades, it might take even longer. Personally, I'm getting really antsy about this. But it's not an unreasonable thing for them to say that the phase space for this search is so big that we just have to listen longer. Having said that, a couple of papers have been published in the past few months from Breakthrough Listen. And these people were looking at effectively entire galaxies, hoping to find evidence of these Kardashev Type 2 civilizations. And remember, if you have access to all of the power of a star, you really can do incredible things. And it seems from these two papers that if those Kardashev civilizations exist, they are very rare. They don't seem to be out there in the local environment.
And that was looking at changes in the infrared spectrum, where the Dyson swarm would change the emissions of the star. How was that done?
This is just radio. So this is classic radio, but if you have that power at your disposal, you can really make a beacon.
Let's dig into this, because I always thought this was a huge question, and you do address it here and there, but I think this really deserves a pointed discussion, which is there's at least two broad categories of possible communications going on out there, assuming there actually are space traveling or communicating societies. One is beacon. Hey, I'm here. But as you point out in the book, it's very expensive to broadcast omnidirectionally. And the other would be, well, actually there's three now. Think about it. One is, broadcast. I'm here. I'm cool. Listen to my rap songs, right? The second would be if, let's say, there are a few hundred communicating civilizations in the galaxy, and it turns out that it is impractical to actually send people or stuff of any sort, that they may be communicating by very tight beam lasers that we're very unlikely to intercept. And so, SETI is, at least today, making the assumption that we're listening for omnidirectional radio. And of course, there's a third one, which is maybe the most interesting, is that if people wanted to, say there are civilizations that want to explore to see if there are other civilizations, they might focus these tight beam, either radio or lasers, at suspect planets and bang them on a very narrow beam, but high, hard to miss. Like if I was doing it, I probably would use something like a laser in some middle of the spectrum near the light range. But we can detect a laser from a really long way off if it's strong enough. And then, and so I think those three approaches to how extraterrestrial civilizations might communicate ought to be informing our thinking around SETI even more than it does.
Yeah, and I think you've encapsulated really the problems there. So it's very energy intensive to send out a beacon. It is a traditional beacon. There are other ways of doing it. You could alter, for example, the spectrum of a star in such a way that people would say, people receiving or taking that spectrum, hey, what's going on there? This is not what we would expect the spectrum of a star to be. But putting that to one side, actually pumping energy into either radio or to laser I think you've encapsulated why it's really difficult. On the one hand, omnidirectional, very expensive. On the other hand, if you're going to target someone, yes, you could do that, but the beam is going to be very, very, very thin. That's why I say there's a huge amount of phase space still to explore. It's a really, really difficult question. Can we do it? Another, going back to sociological examples, is that everyone's listening and no one's actually transmitting for various reasons.
Yeah, and I think I would relate that to another one of the solutions. I was just going to go there next, which is maybe no one is transmitting, and maybe for good reason. And I would connect this to the berserker solution, and then, in fact, I think in the literature I've seen it described as the dark forest scenario. Nobody wants to make a noise in the dark forest because you're going to attract the leopard.
Indeed. Before we go there, though, just to give you again an example of how, if we adopt this Stapledonian approach, we can still look for techno-signatures, even if they aren't actually beamed at us. Okay, so let me give you a couple of examples of that. Suppose civilizations do go and create these Dyson swarms. You put lots and lots and lots of small objects in orbit around your star at 1 astronomical unit, or wherever it is that you feel comfortable, to capture all of that energy, and that's where you live. Okay, so you have a Dyson swarm. What will happen is that the star will appear dim compared to what it should be. Okay, because you're blocking out light. So if we're looking at a star and it appears dimmer than it should be, this could be an example of a Dyson swarm. Now we're entering a golden age of astronomy now. So we have a probe out there called Gaia, which is measuring the true distances, the geometric distances to stars in our galaxy. And it does that by something called parallax. You're all familiar with parallax. If you look at a finger, an outstretched finger with your left eye and the right eye closed, and then the right eye with your left eye closed, the position of the finger relative to a distant background appears to shift. That's parallax. And the angle of parallax lets you calculate the distance. So Gaia is doing this on a galactic scale for a billion or so stars. So we know the distance to these stars. If a star appears dimmer than it should, all sorts of reasons why that might be the case, but one reason a guy called Zacharson pointed out was, well, maybe this is a Dyson sphere. And that's the sort of object that we could then follow up for subsequent observations in, for instance, the infrared, because it would be glowing in the infrared because it's hot. Or even, maybe this is an example of a star that's going to send messages. So it's identifying potential techno-signatures for follow-up. Or if you want to look really, really with a science fictional hat on, a real example of Stapledonian thinking, Clement Vidal recently pointed out that there are these objects in space called millisecond pulsars, and they are effectively incredibly accurate clocks. And if you can lock onto 4 of them, it's giving you a galactic positioning system, these millisecond pulsars. So we have a GPS. So if we ever do go out into the galaxy, and we ever do travel, we have a GPS system out there ready and waiting with these millisecond pulsars. And Clement Vidal says, well, let's put our science fiction hat on. Maybe this has been manufactured by advanced civilizations. Maybe we should be looking at these millisecond pulsars for examples of civilizations tweaking them, or maybe creating millisecond pulsars to create a global positioning system. Wacky, way out ideas, but there are different ways of looking for signals other than just the pure traditional SETI idea of looking for radio.
Yeah, and I do know that the people at SETI Institute, who I've talked to a fair bit, are now putting more effort on techno-signatures of the sort you're describing, which is quite interesting. I'm going to hit two more. I'm just going to read them out because we're running a little bit short on time to get to the last, I think, most interesting part. Two other ones, why we may not be hearing from people, even if they're there. And I love this one because it's so prosaic. Maybe cloudy skies are common, right? That, Earth is cloudy part of the time, and part of the time most places don't have clouds. And if a planet were cloudy, like Germany in the winter, just gray all the time, probably never have any interest, don't even know that there are stars out there. And so even though they may be technically capable of communicating or traveling to the stars, may have a great technology beneath the clouds, they never even think about what might be above the clouds. I don't know if I buy that. Sooner or later, they're going to be curious and send a rocket up and see what's above the clouds, but...
I pop that in because I come from a cloudy place. I don't want to keep going on about it, but it really is depressing here in England at present with the clouds. But on a related matter, we are finding exoplanets. Astronomers are finding exoplanets all the time now. And super Earths seem to be reasonably common. These are Earths that are more massive than our own Earth, but not hugely so. We're not talking Jupiter or Neptune or something a few times the mass of the Earth. Would it be possible if a civilization exists on a super Earth, and there are reasons for thinking that a super Earth actually might be very habitable, would they be able to build a chemical rocket to get off the Earth? Because the rocket equation suggests that would be really difficult. If you have a civilization on a planet that is in a compact system, like TRAPPIST, would the orbits of those planets allow someone like an alien Isaac Newton to develop a theory of gravity? Newton worked on observations made by Kepler about the orbits of the planets in our solar system. If you're in a compact system, people have run various computer simulations of this. You get resonances and perturbations and all sorts of things that make it really difficult to figure out what the law of gravity is if you're an observer like Newton. You need to be on a planet that's got a dense energy source. I mean, it's no coincidence that the past few hundred years has seen a flowering of our civilization because we learned how to extract energy and make use of dense energy sources. It can't be a water world. Dolphins are not going to make rockets, no matter how bright they are. So there's that's slightly flippant, that answer about the clouds, but I think it hides actually something that's potentially quite deep, that there could be civilizations out there that just are not quite on the right planet to enable them to explore.
Interesting. And we'll get to that here in this. That's where we're going to go next. So these last quite a few of these we are assuming that there are indeed extraterrestrial civilizations out there, but for various reasons, they're not communicating. We can't hear them. We're looking in the wrong place. They use very different technologies. They're so different we can't even contemplate who they are. Maybe they live in clouds, like Fred Hoyle said a long time ago. And so they're there, but we can't hear them. Now we're going to go into the one I think is really interesting, and that's that they don't exist. We are indeed alone or it happens at such a low rate, some tiny fraction of one that at any given time, that one would have to wait hundreds of millions of years before there was another one. It only lasts 1,000 years, and then poof. So we're in an interesting little bubble, which is possible. So let's now switch our focus there. And it seems like there's a couple of big themes here in your list. There's 3 or 4 big themes. One is that there may be something special about Earth. Why don't you riff on the various things that might be special about the Earth that would make it not necessarily anomalous that we're special?
So we are finding, as I mentioned recently, or astronomers are finding lots of exoplanets. So that solution to the Fermi-paradox that says Earth is weird because there's not many planets out there, that we know for a fact that is wrong. There are lots of planets out there, but maybe Earth is weird. I think that word is getting some traction in American politics right now. So maybe Earth is weird somehow. Certainly the solar system seems strange compared to many other systems that we've identified out there. That might be just a factor to do with the techniques that we use to discover planets. So maybe we're preferentially finding systems that seem strange to us. But it's possible that the solar system is an outlier, that it's slightly odd. Whatever, you need to have a planet in a habitable zone. We think that life, certainly life as we know it, and it's difficult to talk about life as we don't know it, but life as we know it needs water. So you need to have a planet in the habitable zone, which means it's not too close to the star that the water evaporates. It's not too far away from the star so that the water is locked in ice. And it needs to be continuously habitable, presumably, over billions of years in order to allow evolution to do its work. So you're talking about a planet in a continuously habitable zone. And that's quite strange, given that stars themselves can change in their luminosity over their lifespan. There are hints that the moon our moon might play a part in allowing life to flourish over a period of years on Earth. We've had a billion years of good weather, and it seems that the moon might well have played a role in stabilizing Earth's axial tilt, which means that our climate, by and large, has been quite moderate over a long period of time. It's easy to imagine planets without the stabilizing effect of a moon just going on sort of wobbles like Mars does. And one can imagine life adapting to the cold. One can imagine life adapting to something that's hot. But when you have planets whose axial tilt flips, it goes from cold to hot to cold to hot. And that doesn't seem conducive to intelligent life. And a guy called David Waltham has done some simulations that suggest that the moon it's really in the sweet spot. It's not too big, it's not too small. That's enabled or helped enable climate to endure in a nice, moderate, clement way for a billion years.
Before we go on from the moon, it might be this very odd thing that could answer the paradox, in that there's a couple of different theories about how the moon was formed, but one of the leading ones today amongst planetary scientists is it's the result of a collision very early in the Earth's history with a planet probably the size of Mars. and the moon is the debris from that collision, and such collisions might be exceedingly rare.
Thank you. That's the point I should have made and didn't. That if the collision that we believe created the moon was just slightly different, if that object called Theia had struck the infant Earth at a slightly different angle or at a slightly different time, then the moon would not be the size that it is. The reason it's that size is just a random event. And if it weren't that size, then presumably the climate here on Earth right now would be different. So maybe we're looking for a Earth-sized planet in a continuously habitable zone with a moon that's just the right size. I mean, already you're talking about something that potentially, is quite rare. And the possibilities keep on coming. I'll give you another example. It's not in the book. Some of the things I've been talking about have happened post-publication of the book. But an astronomy group at Cardiff in recent years has been looking at phosphorus in supernova remnants. And phosphorus is one of the 6 elements that we believe are necessary for life. Life as we know it. You need carbon and so on, and phosphorus is another one. And this group, they looked at phosphorus around Cassiopeia A, the supernova remnant, and the Crab Nebula, a different supernova remnant. And the amounts of phosphorus in those 2 supernova remnants are very different. One had lots, the other had very little. Now, if phosphorus reaches planets by means of meteoritic rocks that travel across space, a little bit like that Oumuamua, comes from these supernova remnants, seeds a nascent, a protoplanetary disk, and that's where the phosphorus comes from, then you need to have a planet like Earth that forms around the right sort of supernova. Purely speculative, but maybe there are various elements that need to be in place for life to get going and be maintained over a period of billions of years. And maybe Earth, in that sense, is weird.
Yeah, I think the astronomers, astrophysicists say that our sun appears to be at least a 3rd-generation star, and maybe a 4th-generation star, meaning that it is relatively young as the Milky Way galaxy goes and is built, at least in part, from the outgassings of earlier stars, including the phase of the red giant that happens after the red giant phase produces a lot of heavier elements and, as you mentioned, supernovas. And one of the things may be that we've just been around. This star is late enough in stellar evolution that we have an unusual abundance of heavier materials. And people always talk about the big 6 of elements. It turns out Earth life, as far as I can tell, talking to my Origin of Life people, is surprisingly dependent on another much heavier material, and that's molybdenum.
Yes, and that is an observation that Francis Crick to talk about directed panspermia, going back to our original conversation. One possibility is that we're all aliens, that Earth was deliberately seeded by aliens, a little bit like that Star Trek film with the Genesis planet, that we are the result of a deliberate seeding of life from some aliens 4-5 billion years ago. And it was the presence of molybdenum that led Francis Crick to posit this idea of directed panspermia. The idea of panspermia is an old one, goes back well over 100 years. The idea that life didn't start here on Earth, it fell onto Earth and found a nice place to thrive. But Crick's idea was directed panspermia.
Okay, let's move on. I think there's two last big pieces I'd like to explore, and both of them are worth exploring in depth. And in fact, the framing I like on these two, because it puts them in different places, is Robin Hansen's talk about the great filter. Robin's been on the show a few times. I don't recall if we've ever talked about SETI, but I've talked about a lot of other things. But his great filter idea is that probably the universe is indeed completely dead. And if that is indeed the case, then there's some filter which keeps there from being lots of civilizations. And it either happened before our time, and we were exceedingly lucky. Think of it as the origin of life as one example, as a possibility. And the second is the great filter is ahead of us, which means we've got choppy waters ahead. And I think these two bundles, the first one is it's ahead of us, which you describe as, the galaxy is a dangerous place, planetary systems are dangerous, berserkers, etc. So talk about things that could go wrong ahead of us: berserkers, apocalypse. There's a lot converting to being eaten by the singularity. There's a bunch of things that could happen after us that make civilizations exceedingly rare or non-existent.
Yeah, well, I'm sure your listeners don't need me to come up with those nightmare scenarios. It's absolutely the big question. If there's a filter, is it ahead of us or is it behind us? If it's ahead of us, I mean, where does one begin? Personally, I'm incredibly and increasingly worried about climate change, anthropic climate change. I've talked to quite a few climate scientists, and there's almost an element of despair with them. But let's hope we can do something and solve that problem. There's possibility. There's the grey goo scenario. You mentioned earlier that idea of nanotechnology. Well, if you start manipulating materials at the molecular level and you tell whatever to go and do something, you just need a little bit of a glitch, and that something that it's meant to be making might go wrong, and we just start having these nanomachines turning everything into grey goo. There's hardly needs to say, hardly needs to be said that there's a possibility of nuclear war. I doubt that it would wipe out humanity or all elements of humanity, but it would certainly put a dent in our civilization. Bio war, bioterror is perhaps even more worrying, because if you look at the increases in biotechnology and the science of biotechnology over the past 20, 30 years, it's been incredible. I mean, if computing has undergone an exponential increase, biotechnology, it's faster than exponential. And it doesn't need a lot of imagination to imagine that in 20, 30, 40 years, individuals with a biology degree could create some really nasty pathogens. And if you combine that with someone has bad motives, bad things could happen. You can imagine all sorts of things. So that those are the self-inflicted things. There's a whole bunch of things out there in the universe that could also do for us. Impact events. The dinosaurs were around on Earth and lasted a lot longer than the human species has been around. A impact event did for them. There's the possibility of nearby supernovae. That would not be a good event to be around. There's gamma ray bursters, even more intense explosions. Examples called magnetars. If they come too near, it's not going to do us any good at all. We have a sun that seems to be quite placid, but right now, the past few months, it's been there have been a few solar storms. Nothing too worrying, but I saw the Northern Lights, even though I'm down in the south of England, a couple of months ago. 100 odd years ago, there was something called the Carrington event, where it was a really nasty solar storm. It didn't matter much back then, but in our networked, increasingly computer-reliant technology, if a Carrington event happened right now, who knows what that would do to us. And if it happens in 15, 20, 50 years' time, when presumably we're even more networked, what might be the effect of that sort of thing? So there's a whole load of nasties out there. There's a whole load of self-inflicted wounds that are possible. I have to hope, and I do because I'm generally an optimistic sort of person, that the filter, if it exists, is behind us. And I like to think, and certainly I hope, that we have enough nous and intelligence and goodwill as a species to navigate any of those potential filters, those potential hurdles.
Though, of course, it's going to be timing. We could probably deflect the dinosaur-killing asteroid in 50 years, but not right now. And the Carrington event, I've looked into this quite a bit for other reasons, and EMP, closely related EMP weaponry. There's actually a simple defense that we could harden our civilization against it for maybe $20 billion, but there's never been the will to spend that $20 billion. So we're just sitting there waiting to be zapped by something that astronomers estimate happens about once every 500 years, meaning it has 0.2% chance to happen in any given year. And of course, that number is lower during quiet sun times, and it's higher during times like this when the sun is loud and noisy. So it seems, the way I think about the filter ahead of us, it's a whole bunch of dice rolls. And the problem is it only has to come up once. And it may just be that the combinatorics of all those dice rolls is actually the answer to the Fermi-paradox.
One would hope not. And sometimes it's better not to know things, perhaps, because you scream at politicians, don't you? You say, look, there's a problem here. We could solve it.
Yeah, with the asteroids and the Carrington event, I think you pointed out, and I've seen this done elsewhere, that the risk of dying from a asteroid collision is about on par with flying an airplane the amount of times that a human would fly during their lifetime. So it's not an overwhelming risk, but it's a non-trivial risk, one that we spend billions of dollars to remediate, and yet we're spending finally now little bits on the asteroid defense, but nowhere near enough.
Our understanding of risk might prove to be problematic because we don't have, I think, a good gut understanding of risk and chance and what makes sense to hedge against.
And we're also really stupid about things that are in the future, like climate change, and things where the risk per period, like per year, is small, like the Carrington event or the asteroid, even more so the asteroid. We just don't know how to think about it. It makes evolutionary good sense because if you're a hunter-gatherer dude, your big problem is either not starve to death, be killed by your neighbor, or eaten by a leopard. And so those other things don't really impact much into the fitness function for Darwinian evolution.
Absolutely. But we're in a different situation now, and hopefully, and as I say, I'm an optimistic sort of person. I hope that we make those. It's about getting through, I think, a few decades. The next few decades might be difficult, but if we do, I hope that we have good hedges against those potential filters. And it's it's actually another reason for getting off planet, isn't it? That if you have all of your eggs in this one planetary basket, it makes sense at the species level to spread the risk and get off planet.
That's right. That's Elon Musk's argument. Though it turns out to actually build a self-sustaining civilization that doesn't require Ma Earth to periodically send computer chips and stuff is harder than a lot of these guys are making it out.
This is not something that we can do soon. I mean, the idea even of getting, I think, to Mars, it's mentioned so in such a blasé way. Oh, we'll just go to Mars. Even getting there is incredibly difficult, you know. But I think we have to again adopt that Stapledonian approach. It's not about the next 10, 20, 30 years. It's not about what happens at the individual, the level of the individual lifespan, but over generations. And it's about having the wisdom right now, or our political leaders having the wisdom right now, I think, to try and minimize the risks that we know we do face.
You mentioned the next decades. I don't think we're going to solve some of these problems in the next decades. We'd be lucky if we solve climate, which is a fairly easy one. You know, I look at the next 500 years as a risk window, and then the next 10,000 years as the opportunity window.
Yes, absolutely.
We can probably, if we have any kind of will and intelligence at all, solve many of these future filters in the next 500 years. And if we do, God knows what interesting things we can do in the next 10,000. But beyond 10,000, it's really hard to even think about what might happen. So that is reason to be optimistic if we can get through the next 500.
Yeah, absolutely. Completely agree.
All right, let's turn to the last point, and that is the previous filter. And let's focus principally on life. You know, life, there's lots of different parts of it being a filter. One is that, as we talked about earlier, stellar evolution had to occur for almost as long as it did to produce life on Earth. Couldn't have happened earlier because there wasn't enough molybdenum or there wasn't enough phosphorus or what have you, and now there is. But let's ignore that one. We've already talked about it. But just in the evolution of life on Earth, let's talk about what the previous filters were that we either got really lucky, or let's assume we just got really lucky and got past extremely low probability events.
Let me give you yet another solution that has been posited since the publication of the book. If anyone wants to read the book, please do. But let me give you something new. And that's abiogenesis. And again, I'm not saying that this is in any way likely, but it's an interesting idea, and it gives you some idea of the range of thought about these things. So abiogenesis, we have to get from non-life to life. Yeah, abiogenesis. And a guy recently called Tatani, the Japanese physicist, he pointed out that a definition of life as we know it, if you like, is that of ordered information stored in DNA, RNA. Okay, it's information in there, you get it out, and DNA does stuff with it. But DNA is a very complex molecule, and it's very difficult to understand how that came into being from just chemical stuff that's around there. So one idea, it's not the only idea, but one idea is the RNA world hypothesis, which is the idea that you start with RNA. It's a much simpler molecule than DNA, and it can do both things. It can have a metabolic function, but it can also replicate. Okay, two of the things that you want life to do. So the idea with the RNA world hypothesis is you start with RNA, which is a simpler molecule, and then eventually you go to DNA and the world of proteins and the rest of it that we know and love today. Now, RNA, it consists of, you can think of 4 building blocks, just chains of nucleotides. There's 4 of them, U, C, A, and G. And for the self-replicating aspect, you need about 40 of these things in a chain. Now, if you're adding just these things, these blocks at random, so you have a U, you have a C, you have an A, a G, adding them at random, then there's about 10 to the 24 possible different 40 length chains. And most of those chains are going to have no functional properties at all. Now, that's a massive number, so we're looking for one chain or just a few chains out of that vast possibility of 10 to the 24. If you're just doing this at random, I mean, there may be some principle that we don't understand, but if you're just doing it at random, that you've got these C's in the early Earth, and all that's happening is that these nucleotides are banging into each other, trying to make a chain that can replicate. It's not going to happen. Okay, there's just too many options. There's only 10 to the 22 stars in the universe, and if we're looking for 10 to the 24 possible chains, it's not going to happen. What Tatani said is that the current model of cosmology is that our universe came into being, and at the very, very early part of the universe, there was this event called cosmic inflation. Effectively, for a few microseconds, the universe kept doubling in size. So it got from incredibly small to big in a very, very short time. The idea of inflation was introduced in order to solve various aspects with traditional Big Bang theory. Now, if the duration of that inflationary phase was just twice the length needed to solve those problems for which it was introduced, then the homogeneous universe has a volume about 10 to the 78 times the value of the observable universe. Okay, it will give you about 10 to the 100 stars. So with this idea, you could have huge amounts of life out there. RNA is just banging into each other. The building blocks of RNA just banging into each other by chance. And just that chance process would create vast numbers of planets containing life in the larger homogeneous universe. But within the observable universe that we see, it's just us. So that's an example of an approach to an early filter saying that the transition from non-life to life is rare.
Well, it's interesting. I do talk to a fair number of Origin of Life peoples on the show. We've had Bruce Damer on a few times, and we've had Eric Smith on. And it's interesting, most of them, and then Harold Morowitz as well, who I talked to before I had my podcast, and Stuart Kaufman as well. Their gut tells them that reaching bacteria, while hard, may not be that hard. So let's stipulate that there are. This is kind of an interesting, almost philosophical question. That there are pre-existing trees of catalysis that channel the chemical evolutions in a planet like ours that amazingly lead to life almost every time. Now, if the universe, if the basic particle parameters were slightly different, this would not be the case, but via the weak anthropic principle, they are. And so 50% of the time on a planet like Earth, you get bacteria. Let's just stipulate that. What are some of the pruning rules that come after that?
So first of all, I think it's important to say that might actually be the case. Okay, so this idea that abiogenesis is rare, it's one idea. Equally, there's Origins of Life people who will say, yeah, we can get to life, and these are the steps that will get there. So it's absolutely, I think, a reasonable supposition to say that we can get to bacteria. But if you get to that simple, for want of a better word, form of life, bacteria or single-celled organisms or whatever, as far as we know, are not going to build rockets. You need complex life for that to happen. And that transition from the prokaryotic cell, that simple single cell, to the eukaryotic cell, which enables lots of different things and interesting things to happen. Maybe that's a rare transition. It looks as if you need one primitive cell to eat another cell, and somehow, rather than digest it, find that it makes evolutionary sense to keep it there. Or another cell perhaps infects, is a disease on another cell, and again they have some sort of symbiotic relationship that means that the pair of them function together and can do things that individually they couldn't. Maybe that prokaryotic-eukaryotic transition is rare, and a possible indication that it's rare is given by how long it took that transition to happen on Earth. Now, again, we have just the one example to look at, and that's what happened here on Earth. So it's difficult to draw conclusions. But certainly that transition to complex life seemed to take a long time here on Earth.
And without the equivalent of eukaryotic cells, as you point out, trying to think through how bacteria-level cells could organize into, massive multicellular organisms, just sort of that actually can do something functional other than just sit there, is really hard. And we have the evidence that they haven't.
They haven't here. Certainly haven't here on Earth. It might be a failure of imagination on our part, and everything I've said this evening, it might demonstrate a complete lack of imagination about what the possibilities are. But certainly in terms of life as we know it, I think that's a reasonable supposition that bacteria are not going to do the things we're talking about, travel to the stars or make their presence known across the universe. It's difficult to imagine them doing that.
Our particular variety of multicellularity, life's actually created multicellularity several times, but the one that came out in the Cambrian explosion that led to us may be very rare, and it probably is dependent upon the evolution of the neuron. And one wonders at whether that was just an amazing roll of the dice, or whether life always finds the neuron. And without the neuron, or something equivalent, it's some way to send information signals in a quasi-digital form. It's hard to see really advanced life coming. Next is maybe tool making is rare. You bring that one up, that only one, while many species that we're now learning, and this was not in our textbooks back in the 70s, was it, that a lot of animals do use tools, and a few make very rudimentary tools, but none of them have the ability to use foresight and analysis and improvement in tools the way humans have, certainly in the last 40,000 years of late-stage Homo sapiens. That may be exceedingly rare. It only happened maybe only 40,000 years ago. So after 3.5 billion years at least of life. And then maybe, and you had a very nice little section about the coevolution of tools and intelligence. Maybe if tools aren't developed, or maybe even if they are, intelligence at the human level may be rare. Language could be rare. Hard to say. Again, nobody else has developed the kind of recursive, powerful, symbolic language that we have, and without it, it's hard to see reach. Maybe it's lack of imagination, but it's hard to see getting through the next steps, which is science. The Greeks almost invented science, but if you go back and read Aristotle, which I do fairly regularly, there's a kind of a bizarre mix and melange of good scientific thinking and a lot of theological, metaphysical stuff all wrapped together in one worldview. And it was not powerful enough for the system of science to take off. It wasn't until really Newton that we got, science in a fairly pure form, and without science, getting to the stars is relatively unlikely to happen, or so it appears. Those are a whole series of other early filters that could have been part of the story. If you want to comment on any of those, feel free.
To me, it's not any of the individual potential filters that are important. It's the totality of them. And if you were to ask me, what do I think about the chances of finding other species out there with this combination of abilities, I'd ask why should we expect beings out there to have those characteristics? Why these beings with whom we would share actually only prebiotic chemistry, why would we share those characteristics that define us? This ability to make tools, the ability to think ahead and plan and combine with other members of our species through a language that has a very complex grammar that's enabled us to develop science. And just having opposable thumbs to go around with all of that. Why would we expect to see species out there that are just like us, effectively, which is what we're saying if we're talking about species that want to build radio telescopes or travel to the stars. Those would seem to me the sorts of things, the sorts of qualities that would be required. And it just strikes me as being strange that we would expect to see that out there with these creatures, as I say, with whom we share nothing but prebiotic chemistry, rather than see that same thing happen here on Earth with our cousins and our brothers. The creatures with whom we share the planet, who seem to have no desire to do that. And why would they? Because they're not human. They're elephants or dogs or frogs or whatever it is they are. They're making their living in this universe, doing the things that work for them. We shouldn't expect, I don't think, to find human characteristics out there in the universe.
And then, of course, then the question is, are there other roads to becoming a extraterrestrial communicating society that are very different than the road that we took?
That is what is so fascinating, and that's why, to go right back to the beginning of the conversation, I think trying to find out the role that biology plays and consciousness perhaps plays in the universe is just so important, but also interesting, because absolutely, I may be completely wrong, and maybe there are many different roads that one can follow. And I would love to live in the sort of science fiction universe that was described by Star Trek and Forbidden Planet and all that science fiction that I read as a kid. That would be wonderful. And I think we need to get out there and try and find it.
Yep, indeed. All right, let's now come to your actual conclusion. You kind of hinted at it in passing there, but let's say it explicitly. Your solution number 75, after saturating yourself in this stuff, seems like more than anybody I ever ran into. You've been thinking about this long and hard for a long time. What is your bet? If you could go down to the bookie and put a bet down, and in 5 years the answer would become clear, what would you put your money on?
I would put my money on being alone. When I wrote the first edition of the book, part of me thought I'm going to be exposed as the world's most stupid man, because I'm just saying that I think we're alone. And people like Frank Drake are saying, no, we're going to find evidence really very soon. Part of me still thinks maybe I will be exposed as being spectacularly stupid here. Part of me wants to be exposed as being wrong, but if I had to bet, I think we're alone. And I think it is then very, very, very strange when you look up at the night sky and you see how big the universe is, to think that it might just be us. I think it then puts a huge moral responsibility on humanity, because we would be, and as far as we know, we are the only bit of the universe that has come to know itself, in those wonderful words of Carl Sagan. And I think it's then just incumbent on us to really try and survive those decades and the risky period ahead that we discussed, Jim. I think it's really incumbent upon us to make sure that only part of the universe that does know itself continues to exist and to know itself.
Well said. In fact, I have another life where I'm involved in a radical social change movement to try to save humanity. And the way I frame that is that we're at this fork, which isn't too far away, where we'll have a pretty good sense of whether we're alone or not. And we don't know currently, but 500 years, we probably have a pretty good idea based on atmosphere analyses, et cetera. Maybe even send a few probes out. We might find life on one of the Jupiter's moons, which would change the math a little bit. But until we know, we ought to act on the precautionary principle that we are alone. And it would be a gigantic moral failure to allow this one thread of general intelligence to lapse in the universe.
Absolutely. I could not agree more.
Well, I want to thank Stephen Webb, author of If the Universe is Teeming with Aliens, Where is Everybody? As usual, there'll be a link to the book and many of the topics we talked about on the episode page at jimruttshow.com. And I want to thank Stephen Webb for just the most amazing, interesting conversation.
Thank you, Jim. It's been a pleasure.
It really has been. Audio production and editing by Andrew Blevins Productions. Music by Tom Muller at modernspacemusic.com.